Okay, so today we're going to be covering problem number 6 from the 1999 exam on the BC test. This is a type 7 problem, and I qualified it as type 7 because it's kind of the miscellaneous category, and Euler's method usually is done on either a type 6 or type 7 question, type 6 being separation of variables. We also are doing some tangent line linearization type methods, and even some fundamental theorem of calculus. So it's a little grab bag, not real focused on the topic overall through all three parts. As I said, this is from 1999, and it's the BC question number 6. So starting off with part A. So let the function whose graph goes through the points 3, 6, so they're telling us an initial condition, and whose derivative is given by f prime of x equals this. Write the equation of the line tangent to the graph at 3 and use it to approximate f of 3.1. So we're doing two things. First off, we are going to write the tangent line approximation. And using Taylor's form, the tangent line approximation is f of the center plus f prime of the center times x minus the center. And they told us that the center is at 3. In other words, use the tangent line at 3 to make the approximation. So the first thing we need to do is find f prime of our center. So f prime of 3 is equal to 1 plus e to the third over 3 squared. Okay. And if you grabbed a calculator and typed this into the calculator, you'd find that this value is approximately 2.342, or 343. Okay. So let's create the tangent line approximation with the information that we're given. L of x is f of the center, so what is the function at the center 3? The function is 6 at the center 3, so f of 3 is 6. F prime of 3 is, I'll put down the exact value. That's f prime of 3 times x minus our center, which is 3. So there's our tangent line to the function, and we will use this to approximate f of 3.1. So f of 3.1 can be approximated by L of 3.1, and L of 3.1 is equal to 6 plus the quantity 1 plus e to the third over 9 times 3.1 minus 3. Now this is a numeric answer, and it is sufficient to earn you credit on the problem. Of course, some people like to simplify their answers, and if we were to do this quotient and multiply it by 0.1 and add to 6, we'd arrive at 6.234. So f of 3.1 is approximately 6.234. Now remember that it's not exactly equal to that. That's an approximation. So that's part A. Part A is worth 3 points, and the 3 points come from first evaluating f prime of 3. When you get that value, that's 1 point. The second point comes from setting up the tangent line equation. So that's 1 point. And then the final value comes from, did you correctly approximate f of 3.1? So 3 points overall in part A. All right, let's move on to part B. Part B says, use Euler's method starting at 3 with a step size of 0.05 to approximate f of 3.1. So we're now taking a different approach to approximate f of 3.1. In the first case, we used linearization techniques to do this, and now we're going to use Euler's method, which is basically an advanced form of linearization. You're doing several smaller increments of lines. So that's the first part, and the second part says use the second derivative to explain why this approximation is less than the true value. So Euler's method, different approaches for different classes. The approach that I teach in my class is to create a table that we use to track the values. And the xy, m is your f prime of x, or your dy dx. Your delta y is equal to m times the delta x, and your new y value is equal to the original y value, or sorry, the last y value, plus your delta y. And when you're filling out this table, you need to have a starting value or initial condition. And in our case, the initial condition was given as 3, 6. So 3, 6 is where we start. Okay, advancing through the rest of the table oftentimes can be done by hand, but in this case, this is a calculator active question, and it's probably going to be much easier to do with a calculator. Finding the slope, the approach that I took, and it's not the only way, is I wrote the slope equation as my y1, and then if I go to the table value and I find out what is the slope when x is 3, oops, let's change our table setup to ask. Okay. So when x is 3, we get a slope of 2.3428, and it's probably worth putting in more decimal places than 3. Or what we could do is we could evaluate it from the home screen by going y1 of 3, okay, and that gives us the same value. And this is the approach that's going to be most beneficial for this table, because our next step is to take that answer and multiply it by our delta x. Well, they told us our delta x was 0.05, so let's take that answer and multiply it by 0.05. And we get 0.117418. And then we add that to the old y value, so y plus our delta y. So we're going to add that to 6. 6.117141. Okay. So our next step is at 3.05, and then this value comes down here as 6.117. Okay. I want to plug this equation into my slope function, so I'm going to do vars, y vars, function y1. So we're evaluating f prime at our at our x value of 3.05. And that gives us the slope here of 2.37735. This number gets multiplied by our delta x, which was 0.05, m times delta x, 0.11886, and then this number here is added to that y value, which I have right there. So I'm going to do answer plus, and I can highlight that value. Answer plus that value gives me my new y value of 6.236000962. And then one step later, 0.05 further along is 3.1. This number here comes down 6.236. And this is the table for Euler's method. So by Euler's method, we've approximated that f of 3.1 is approximately 6.236. And that's with a delta of x of 0.05 2 steps. So this part of the problem is worth 2 points. The first point comes from using Euler's method or some sort of Euler's method table. There's different approaches, as long as you're demonstrating an understanding of Euler's method. And then your second point comes from correctly getting the value approximation for f of 3.1. So there's our 2 points for part B. Now if we look at part B, you'll notice that part B says two things. First, approximate, and then use the second derivative to explain why the approximation is less than the true value. So if it's asking us to use the second derivative, then I'm going to need to find the second derivative. So f prime of x is 1 plus e to the x over x squared. If we do the second derivative, there's a quotient, so I'll need to apply the quotient rule. The quotient rule is the derivative of the top times the bottom, subtract the derivative of the bottom times the top, all over the bottom squared. So we have our second derivative here, and we're going to use that to make statements about the approximation that we found. So if you'll notice that on this second derivative, on the interval 3 to 3.1, which is where we started and where we finished, the second derivative is greater than 0. So let's take a look at how I made that assumption, because I didn't really show the values of it. Let's simplify the second derivative. If we go through, we have e to the x times x squared, e to the x squared minus 2x minus 2x e to the x over x to the fourth. You'll notice they all have x's in them, so we can pull an x out. E to the x times x minus 2e to the x over x to the third. And finally, if I do one more simplifying, this is x minus 2 e to the x minus 2 over x to the third. Any number greater than 2 plugged into this will be positive, so all the values from 3 to 3.1 is a positive number times a positive number. E to the third power is, roughly 9, so positive number times a number greater than 9 minus 2. The numerator comes to a value of greater than 7, roughly. So we know it's a positive number and the denominator is always positive. Therefore, the second derivative is always positive. So on the interval 3 to 3.1, the second derivative is positive. Therefore, f of x is concave up on 3 to 3.1. And Euler's method approximations will be below the true value. Okay. So to recap, they wanted us to use the second derivative to show that the approximation found here was less than the true value. So because the second derivative is positive on the interval of Euler's method, the function is going to be concave up. And when your function is concave up, Euler's method is below the true value. And graphically what's going on is you have a curve that is concave up, and at an initial condition you did an Euler's method step that took you to here, and then an Euler's method step that took you to here. And so this is our approximation, and this is the true value. So that's why we know that on concave up curves, Euler's method under approximates. Similarly, on concave down curves, Euler's method will over approximate it. So the breakdown for the 2 points here on this portion is step 1, you get 1 point if you correctly found the second derivative, and then part 2 of that would be if you were able to explain why that second derivative informs us that the approximation is below the true value. All right, let's move on to part C. Part C says use the definite integral 3 to 3.1 of the derivative to evaluate f of 3.1. And this is fundamental theorem of calculus in action. I like to write this as f of b equals f of a plus the integral a to b of f prime of x dx. Or I say what I have is equal to what I started with plus what I accumulated. Okay? So in this case, where our accumulation is going from 3 to 3.1, and we're finding the value of 3.1. F of 3.1 is where I started plus what I accumulated from my start point to the value I'm approximating. And we are seeking out this answer of f of 3.1. f of 3 is given to us. It was the initial condition stated up here. So f of 3 is 6. And the integral is a equation that we can type into the calculator to evaluate that definite integral. So if we go through the process of typing this into a calculator, since I already have it stored in my y1, I'm going to call on that. I'm going to say math 9 from 3 to 3.1 of the function y1. So if I press alpha F4 or alpha trace, that pulls up my y1. I can also do it through the vars menu, but with respect to x. The integral evaluates to 0.2377, so plus 0.2377, and we find that f of 3.1 is, I'm going to use the approximately symbol because we're rounding the decimals, 6.238. So they'd accept 6.237 or 238. Okay, the points breakdown for this portion is you get 1 point if you use the fundamental theorem of calculus, and you get 1 point if you correctly evaluate the answer. So there we go. That's question number 6 from the 1999 exam. And as my students say, be sure to comment, like, and subscribe. Have a good day.